So welcome to this class. And this short video, we're going to discuss about elementary operations and determinants. So we'll start by giving some properties of operations and how they relate to evaluation of determinants, and then do an example to illustrate how you use row operations to find determinant of a 3x3 matrix. So theorem. Let A and B be square matrices then one, first property, if B is obtained from A by interchanging two rows of A, then this is how the determinant of A and B are related. Determinant of B is equals to negative determinant of A. So for example, given that A is this matrix 2 minus 3, 1 and 4, then interchanging row 1 and row 2, we have 1, 4, 2 minus 3. Unless this new matrix be B. Then if we find the determinant, so this is an example to illustrate this property. Determinant of A, for these are 2 by 2 matrix, will be 4 times 2 minus 1 times minus 3. So this 8 plus 6 plus 3, which is 11. That B will be 1 times minus 3 minus 2 by 4, which is minus 3 minus 8, which is minus 11. So clearly, with this demonstration, you see that determinant of B is the same as negative determinant of A. So that's what we're saying in that given property. So anytime you interchange two rows, then the sign of the determinant becomes negative. Property 2, if B is obtained from A by adding a multiple of a row of A to another row of A, then this is how the determinants are related. Determinant of this matrix B is the same as determinant of A. So it doesn't change the value of the determinant. Adding a scalar multiple of one row to another. And then you demonstrate by an example. Given A is this matrix 2 minus 3 and then 1 minus 4. So let's say now we have this matrix. So A is given by 2 minus 3, 1 minus 4. And then I say, let row 1 to be row 1 and row 2 to be row 2 plus minus 2 row 1. So that my new matrix will be 2 minus 3, 1. Actually, I say negative a half of the first row, so that I get 0 in the second position, the lower row. First position, this row here, negative a half. So I'll get I'll get 0, and then minus 4 minus, actually, so it'll be now plus 3 over 2. So I have now negative 4 plus 3 over 2. That will give me minus 5 over 2. So assuming that I got this matrix, this new matrix after this operation, I call it B, then we can see that the determinant of A will be given by 2 times minus 4 minus 1 times minus 3, which is minus 8 plus 3, which is minus 5. And the determinant of B is 2 times minus 5 over 2, and then minus 0 times minus 3, which is minus 5 plus 0, which is minus 5. You see, this and this are the same. And even if I obtain another matrix C by saying I multiply the first one by row 1 and then row 2 to be, say, negative 2 over 5 row 2, then C will be 1. This will be minus 3 over 2. Then this will be 0. And then this, if I obtain this one here now, I get now this one will be now positive 1. But this now will be different because now I was not adding a scalar multiplication of one row to another row. So that's why this will be different. But then if you do what we have done in the first case, then that will give you matrices that have the same determinant. So the key thing is that if you take a scalar multiple of one row and add it to another row, the resulting matrix is having the same determinant as the original matrix. And then 3, if B is obtained from A, by multiplying of a row of A by a non-zero scalar constant C, then determinant of this matrix B is the same as this scalar times determinant of the matrix A. The key word here is if B is obtained from A by multiplying of a row of A by a non-zero scalar. Then the determinant is given by determinants are related by this. So for example, if I have my matrix A to be given by 2 minus 8 minus 2 and then 9, and then you see that I can say this first row 2 is common. So I say I have B 2 so I have another matrix. So because 2 can be factored out in the first row, so I can say if I get a matrix, so when I take out the 2, I'll have 1 minus 4 and then minus 2, 9. So determinant of A will be given by 2 by 9 and then minus 2 times minus 8, so which is 18 minus 16, which is 2. And determinant of B is 1 times 9 minus 2 times minus 4, which is 9 minus 8, which is 1. And you see the determinant. So we said if this property here that if B is obtained from A by multiplying of a row of A by a non-zero scalar constant C. So you see in this matrix A, we obtain this one by multiplying a half times this row of A that gives us this 1 and then minus 4. So you say determinant of B is the same as that half times determinant of A, which is a half times 2, and you get 1. Or we can have another example. If A is this matrix 1, 2, 6, and then say 8, and then I have B, let me say this is 16. If I have B as 1, 2, and then 2, 1, you see this row here is obtained by simply multiplying this one by 1 over 8. So determinant of B is the same as 1 over 8 determinant of A. We can see this one. So determinant of B is 1 times 1 minus 2 by 2. So 1 minus 4, which is minus 3. Determinant of B of A is 1 by 8 minus 2 by 16. So 8 minus 32. So this is minus 24. You see 1 over 8 times minus 24 gives us minus 3 as the determinant of this other one here. So with these properties now, let's do a specific example. So use elementary row operations to obtain the determinant given A is 2 minus 3, 10, 1, 2, minus 2, 0, 1, minus 3. So solution, because you know that if the matrix is in triangular form or echelon form, then we have to get the determinant as we multiply just elements along the main diagonal. So this being a 3 by 3, so expect to have this staircase. Staircase pattern. Now, that's what I would expect to have something like this, that we have an upper triangular matrix. So this may be non-zero elements, but then this is what you have. So you can say determinant of A, which is denoted by this 1, 2, minus 2, 0, 1, minus 3, is the same as negative 1. So I interchange these two rows. I write here 1, 2, minus 2, 2, minus 3, 10, and then I fix this row 3. So what I've done is that row 1 has been interchanged with row 2. Row 2 and row 1 have been interchanged, and then row 3 remains to be row 3. So this interchanging is what leads to this negative. We saw in the first property that interchanging any two rows changes the sign of the determinant. And then remember, these are signs for a determinant. And then, so next one, we say this would be negative 1. So 1, 2, minus 3, minus 2, 2, minus 3, 10, 0, 1, minus 3. So I say row 1 to be row 1, and then row 2 to be row 2, plus minus 2, row 1, and then I say row 3 to be row 3 for the start. So that leads me to negative 1 is just there. So 1, 2, minus 2. The 2 plus minus 2 times 1 is 0. Minus 3, minus 2 times 2. So minus 3, minus 4, minus 7. And then 10 minus 2 times minus 2. I have 10 plus 4, which is 14. And then this one is 0, 1, minus 3. And then this one here, I can factor out this row here. 7 is common, so factor out 7. So I have next step, factor out minus 7, so that I have, so minus 7 times minus 1, I get positive 7. So 1, 2, minus 3, minus 2, 0. Now this will be 1, this minus 2, 0, 1, minus 3. Now I fix row 1 to be row 1, row 2 to be row 2, but row 3 I say to be row 3 plus minus 1 row 2, so that I have this one to be 0. So that leads me to determinant 7, 1, 2, minus 2, 0, 1, minus 2, 0, 0, minus 3, minus 2. So I get this plus, so minus 1. Now this is in triangular form. So this triangular. So when it's in triangular, then it's very easy to just get the product of elements along the main diagonal. So therefore, determinant of the original matrix A is 7 times 1 times 1 times negative 1. And the answer is minus 7. So that's what we have. And then theorem. This theorem illustrates cases whereby you can get zero determinant. So just say conditions that leads to zero determinant. So so we say if A is a square, a matrix, and any of the following conditions is true, then determinant of A is always zero. So these are the cases of the conditions. One, an entire row or column consists of zeros. Either like this one, 0, 0, 1, 2, or if you have a matrix like 0, 0, 1, 6, or if I have a matrix like 1, 2, 0, 0, 0, 4, 8, 9, 10, or if I have a matrix like 0, 0, 0, 0, 1, 2, 4, X, W, 1, 2, 4, 8, 1, 3, 9. If I have 0, 0, 0, 0, 2, 8, 1, 3, 2, 4, 5, 6, 1, 8, 1, 9, 10. You don't care. Once you see that a column has all zeros or a row has all zeros, then determinant of all these matrices are zero. Number two, two rows or columns are equal. Like if I have 3, 4, 8, 6, 9, and then 3, 4, 8, or I have 10, 6, 7, 1,000, 100, say 4, 9, and then I have 10, 6, 7. The determinant of all these matrices is 0. So I have 9, 6, 9, 6. All these have determinant 0 because they have some rows or some columns which are the same. And lastly, number 3, one row or column is a multiple of another row or column. So e.g., if you have 6, 3, 12, and then I have this one to be 6, then determinant of this matrix 6 by 6 minus 12 by 3 is 0 because this is a scalar multiple. I will multiply this column by 2 to get the same first column. But we have 1, 2, 3, 4, 2, 8, 6, 8, say this 4, and then 6, 9, 10, minus 11, 2, 9, 10, 14. You don't have to go into cofactor expansion or row operations, because this and this one have a scalar multiple of each other. Then determinant of this one, if this was matrix B, determinant of B is 0, because this and this are scalar multiple of each other. So those are the conditions that yield zero determinant, and they can always help you to know the value of a given determinant without really struggling to do the calculations. And then last theorem, if A is an n by n matrix and C is a scalar, then the determinant of CA is given by that CA equals to C power n, determinant of A. So e.g., if I have A given by 10, minus 20, 40, 30, 0, 50, minus 20, minus 30, 10, then it's clear that this can be written as 10 into 1, minus 2, 4, 3, 0, 5, minus 2, minus 3, 1. And determinant of 10, minus 20, 40, 30, 0, 50, minus 20, minus 30, 10 will be the same as now. This is a 3 by 3 matrix, so our n is 3, the same as 10 power n, which is 3, determinant of 1, minus 2, 4, 3, 0, 5, minus 2, minus 3, 1. And when you work out the determinant of this matrix, you get 5. So this would be 10 power 3 times 5, which would be 5,000. And another thing that you need to actually, that can help you to reduce a lot of calculations when you're doing determinants, it's always good to use columns or rows that has 0 elements, so that you can actually ignore some cofactors, because multiplying 0 element by any given determinant gives you 0. So like for us to get the determinant of this one, it's easier to use row 2 or say column 2, so that we at least this has 0, so that we just have 2 determinants to evaluate. So thank you.